So let's try to draw this and then take a look at this. Okay. So I'm just drawing a scenario, okay, because we don't exactly know what is our A and B are. And what we want is the largest area that inscribe a rectangle that can be described it. So what we know is x and y, and if the ellipse is something like this, right, and we know that, you know, this will be where my A is, and this will be where my B is. Okay. And let's call this point right here, right? Let's call this point right there X and Y. So the idea is this. We want to find out the largest area that inscribed in here, but however, that will be too much work, and that will be also like, you know, a problematic when this point move around, right, to the second quadrant or third quadrant or fourth quadrant. Then it becomes plus or minus sign is a lot of like, you know, problematic for us to, you know, keep track of it. So the idea to attack this type of problem is basically looking at only this area in the quadrant 1. And we want to find out the largest area in this quadrant 1 so that later on I can just basically multiply by 4 to get what? The entire rectangle. Are we all following so far? The idea? We good, right? Oh, crap. So because of I'm putting this point as x and y, so what's going to happen is I will get, this is my x distance, and this is my y distance right there. Okay. So that will help us to write, you know, something from here on. Questions, difficulties before we move on? All right.
This meeting is being recorded.
So for example 4, we want to find the area of the largest rectangle that can be inscribed in the ellipse. Okay? And the ellipse is not given to you a specific ellipse, it's in general. So we're going to make assumptions of like, you know, it's a vertical ellipse. It could be horizontal, but, you know, doesn't really matter. But what we are interested in is the largest area that can be inscribed, the rectangle that can be inscribed, right? And then giving you the largest area. So what happens is we know that, you know, in an ellipse, this will be my A, right? This vertex will be my A, and this vertex will be my B. And this, the point on the ellipse and then the vertex of this rectangle, you'll call it XY because we don't know where that is, you know, to make it a maximum, the largest area, right? So once this point XY is in the quadrant 1, that's not a problem. But once it becomes in quadrant 2, quadrant 3, or quadrant 4, right? Then what's going to happen is we need to really keep track of our negative and positive x and y. So that would be too much problem for us. So the idea to attack this problem is looking at the rectangle in this quadrant 1, and then find out the largest area of this rectangle in quadrant 1, and then later on we multiply by 4 to get the whole picture. Okay? So because of like, you know, this is like in quadrant 1, this rectangle, the length will be x, and then the height will be y, right? That's what we're going to be using. So our objective functions will become, right? Our objective function become what? The largest area, That's our objective function, which is easy. The area of a rectangle is length times width. What difficulty part is like there's a lot of variable involved because A and B, although those are fixed number because of its written in general, we don't know what A and B is. So now we need to write it. Let me change this variable, right? My length and my height, right? So that way I'll have X and Y so that it will be consistent with this. So what we're going to do is we're going to try to rewrite this area function in terms of one variable. So that means I need to either solve for, substitute y in terms of x or x in terms of y. So what we want to do is we want to try to this time change a little bit. I'm going to write a function of area in terms of y. So we're saying that already, deciding that already. Then what we need to do is we need to substitute x, right, in terms of y. So what can we do? Basically, this x and y, those two, order pair, is on the ellipse. So therefore, I can use this equations to solve for x. So let's try to do that.
The recording has stopped.
So I have x squared over a squared plus y squared over b squared. That is equal to 1. So when I solve for x squared, that will become x squared over a squared. That is equal to 1 minus y squared over b squared. And I multiply both sides by a squared and then take the square root. Right? So that will become a squared minus a squared y squared. Let's do this. Let me write it in factor format. A squared times 1 minus y squared over b squared. Okay. So now what's going to happen when I take the square root, this will become my x could be plus or minus, and square root of a squared is a, and then I will put the square root inside of this y squared over b squared. Since we're going to be talking about in a quadrant 1 only and looking at this little shaded rectangle, so both of my x and y's are positive, so I can ignore that negative portion. Right? So now what I can do is I can basically substituting with x with this a times with square root of 1 minus y squared over b squared times with y. So that's what I got. So now next step, what we're going to do, this is going to become a long process and a little bit more difficult to use the first derivatives to test it, right? So, but we're going to try that. So what we're going to do is now we're going to try to take the derivatives and then find out the critical numbers. And with the critical numbers, then we will need to justify that critical number is a minimum or maximum by using the first derivative or second derivative test. So for this problem, I'm going to still use the first derivative test, right? To show you how tedious can be on the work. And then after that, we can conclude, what is the largest area. So let's try that.
This meeting is being recorded.
Is there any questions so far? Are you all okay with this? Okay. So taking the first derivative, a prime of y, right? And that will give me, remember, a and b's are the constant, right? So first I'm going to use the product rule and then take derivative of y, which is going to be a. I'm going to rewrite it as a power, so that way it will be easier for us to take derivative later on. B squared to the 1/2 power times with 1, using the product rule, which will be plus. Okay? Then this times the second factor, right, times with when I take derivatives of the second factor, the first factor, which is a power first chain rule, right? That'll be a times 1/2 1 minus y squared over b squared subtracting 1, so it will be negative 1/2. And times with derivative of inside, which is going to be 0 minus. And remember, derivative inside is basically just taking derivative of y. Okay, so that will become 2y over b squared. Right? So that's the derivative of this. Any questions before I move any further? Because a and b's are constants, right? In an ellipse. So simplifying a little bit on this so that it will make it easier for us to continue. So my a times 1 minus y squared over b squared to the 1/2 power minus, okay? Now y minus this negative sign right here and positive sign right here will become negative. This half and this 2 will be cancelled out. And then y times y is y squared. So I will get this a y squared over b squared times with 1 minus y squared over b squared to the negative 1/2 power. Any questions before I move any further from here?
Wait, why does it stay at b squared?
You're talking about in blue or in black one?
The blue one.
Oh, because this is a function. B and a's are constant. Y is the variable, so we are taking derivative of the area functions respect to y.
Oh, okay.
So, from here, when you look at it from here, right, you're taking derivative of only what? Y squared part, which is going to become 2y. Any other questions? So now, what we need to do now next is what? Find out the critical value, right? So looking at a prime of y equal to 0, so that will give us what? Critical number. So when a prime is equal to 0, right? That is basically talking about this portion equal to 0, right? So which is what? A times 1 minus y squared over b squared to the 1/2 power minus ay squared over b squared 1 minus y squared over b squared. That is negative 1/2, which is equal to 0. Okay with this? Now, this is where we need to, this is where we need to be careful, right? So take a look at on this, what I'm going to be doing. First, I'm going to divide everything by a, so that this will be gone. A will be gone. So it will become 1 minus y squared over b squared 1/2 power minus y squared over b squared 1 minus y squared over b squared to the negative 1/2. Right? I divide everything by a. So now the next step is how do we get rid of this negative 1/2 power? So basically what we do is we multiply, okay, both side by, right? We multiply both side by this. One minus y squared over b squared 1/2 power. Okay. So multiplying both sides by this 1/2 power, take a look at this, the first term, and half power times half power, right? When the base are the same, you add the exponent, it becomes 1. So that will become 1 minus y squared over b squared to the 1 power. Minus y squared over b squared. And base are the same, so when you multiply it, negative 1/2 plus 1/2, that will become what? 0, so which will become times with 1. 0 times anything is 0. So you need to be able to simplify, using all the rational exponents and stuff. Okay with that? So from here, when we simplify further, this will become 1 minus, since 2 of them, so it will be 2 over b squared y squared equal to 1. Equal to 0, my bad, sorry. So you add 1 to, from here, you subtract b's, 2 over b squared y squared, both sides. So this will become 2 over b squared y squared. And then you multiply by reciprocal and then take the square root. Right? And you multiply by reciprocal and then take the square root. That will become b squared over 2 equal to y squared, and then y will become plus or minus square root of b squared over 2. And we want only on the quadrant 1, so it will be just what? A positive part, which is going to be b over square root of 2. So that's our critical number. And now what we need to do is we need to test this critical number. We know that the value of y cannot be 0, and the value of y cannot become b. Because if you look at the ellipse, if the y value is become b, that will become just a line. It is not a rectangle anymore. You cannot form a rectangle. Okay? So that's the restrictions right here that you need to know. So therefore, right here, we have this b divided by square root of 2. That is approximately 0.7 b if you use a calculator. So that I can basically test, 2 numbers right here. So, is there any questions before I move any further from here? Are you all okay with this? So, let's test it. If I test this, okay, I need to choose what? A point. What we are testing? We are testing on the value of what? The a primes of y, the derivative functions. Okay? So what we're going to test is we're going to put it in like, we can put 0.5b. We can test that. And we can put 0.8b. We can test that. So this is where it's going to be a little bit, tricky. You need to follow carefully right here. And try to test it in here. So substituting y with this 0.5b and then so on and so forth. Ready? So if I plug it in this 0.5b, right, into here, let me do this. Give me a second, okay? So this is a prime of y. So when I test, a prime of 0.5b, take a look at on this. Technically, I will not write it down, but to help you to see on the first one, I'm going to write it down so that this will be 0.5. Y is basically 0.5 b squared, right? And then b squared to the 1/2 power minus a times 0.5 b quantity squared over b squared, 1 minus 0.5 b, right, quantity squared over b squared to the negative 1/2 power. So look at right here. This b squared, when you square it, b squared and b squared will what? Cancels it out, right? And then that's 1.25. So you will get a positive value right here because 1 minus 0.25. So that will become 1 minus 0.025. No, not 0.25. 1 minus 0.25 to the 1/2 power. And right here also it will cancel it out, right? B squared, so it will be 0.25 a, and times 1 minus 0.25 to the negative 1/2 power. Are you all following so far? So I don't know what the value of a is, but what I can do is from here I can factor a out. And then when I compute just inside part, this will be 0.75, square root of 0.75 minus 0.25, right, times with 0.75 to the negative 1/2 power. So when you compute this, what is this value? Remember, a is always a positive number, okay? So when you compute this, what is the value that we get? Are we all following what I'm doing? Is there any questions? Okay. If you're good, then this will be square root of 0.75 minus 0.25 times with 0.75 to the negative 1/2 power. Okay. Syntax error? What did I do?
I got 0.57.
Square root of that is 0.6 what?
57 is what I got.
I also got 0.577.
So the key thing is we got a positive number, right? Positive number, agree? Because this number, a positive number times a positive number, that will be what? A positive number. Are we all following so far? Yes, no?
Yes.
Now, if you understood this, then I can change it very quickly and then you can see what's gonna happen. If I plug it in 0.8, and this will become point. What the hell? How come it doesn't work anymore? Anyway, I'm gonna change this right here so that I can use it. So if I put it into 0.8 right here, that would become 0.64. Agree? And this will be 0.64. And this will be 0.64. So what happened is we are getting something different right now. Right? So this will become square root of 0.36. And this will be 0.64. And then this will be 0.36 to the negative 1/2 power. And from here, you can see that we will get like a negative number. So try to compute this part now. So square root of 36, right? And then 0.64, and then you time it.
I got 0.183333.
Negative, right?
No, did I do it wrong?
I got negative 0.46.
I got negative 2. Okay.
Let's see here.
So when I plug it in this, that will become negative 0.466 something. So what we do is like we know that this will be negative sign. Do you see that as tedious right here when we checking this first derivatives? That's the reason why I put this example. You know, sometimes like it can go that far using the first derivative, second derivative. But do we all follow what I'm doing? Right? We do the same thing, but however, because we don't have numbers anymore, it becomes very tedious. And at this level, we need to be able to work on these kind of problems. Okay? So, are we all okay with this?
It is very tedious.
It is. That's why I'm saying this is going to be a long problem. That's what I'm saying. Because of showing in detail like this, at least like first time you need to see it so that you see it's workable. And the important part is right here, my B has to be upper bound. You cannot go over B because that will not form a rectangle anymore. Are we all okay with this? So from here, what we get is what? Now that we know, right? By what? First derivative test, right? By first derivative test, the area is at maximum at when y is equal to what? B over square root of 2. And what is the question asking for? The question is asking for find the area, right? Find the largest area that can be inscribed. So what do? We just basically plug it into the formula, right? But however, remember we are only doing what? A tiny rectangle. So the largest area that must be done with what? 4 times the area of what? B divided by square root of 2. So that is basically 4 times when I plug it into the area functions, right? Area function, which is going to be what? A times square root of 1 minus B divided by square root of 2 square all over B square times with B divided by square root of 2. And this will give us, after you simplify it, this will give us 4a, right? And if you look at right here, b squared and b squared, they're going to cancel it out. And this will become 1/2. So that will be square root of 1/2 times with b over square root of 2. So square root of 1/2 is basically 1 over square root of 2. When you multiply square root 2 and 2, square root of 2 is 2. Reduce it with 4. That give us 2ab. That is my maximum area. So this is a very, tedious problem on checking justifying the, justifying the maximum and minimum part on your critical value. So, any questions on this? Are we good? Okay. So So if we are done, then I'm gonna stop right here. And example 5 is very similar to this problem, but however, is like a little bit more manipulations. That one I will post it right for you on a video lecture later on, because I forgot to record this one. I think I didn't record it. No, I did not. I don't even remember where I stopped it.
What are you worried about?
Huh?
What are you worried about?
I don't know where I stopped this one because I forgot to record it.
I recorded it.
Oh, you recorded it. But I need it.
Okay. I will upload it to YouTube and send you the link, and you can embed that link onto your class website.
Anyway, I can record it anyway later on. So I believe I stopped right here. Yeah. So yeah, I stopped it right here. I think I remember. Okay, so so you can see that it's very tedious on this one. Okay, and example number 5 is a very similar problem like this one. Okay, but those are more of like I would say they're close to advanced type of problem, right? In my opinions, because it's a little bit more tedious one, but it's still doable, right? Still doable. It's not the advanced type of problem yet, I think. No, there's like I have run into something that is harder than that, but I'm not really sure your textbook will have those kind of problems. But on a test, once again, it will be 2 problems from here. One will be elementary, one will be intermediate, right? Like before. So definitely you will get 2 problems from these sections, at least. Any other questions for me?